Okay, let's go ahead and solve this thing. I'm going to start out with a result from differential equations course. You'll find that the general solution to a non-homogeneous differential equation like this, non-homogeneous meaning that the right-hand side has some term. It's not zero. The general solution, y, well, let's call it x in this case. X is equal to two parts. A complementary solution plus a particular solution, where xc is the solution to the homogeneous form of the differential equation. That's the solution to homogeneous equation, which is just, it solves mxc double dot plus cx double dot c plus kxc is equal to 0. The complementary solution solves this equation. We already have that solution. We solved for it when we were figuring out the unforced system, what the solutions to it. xc, that's like the that's the decaying exponential. That's this thing, at least when we're talking about damping ratio being less than 1. Okay, this is our complementary solution. That's what we're talking about there. Turns out that if we can find any solution, xp is a particular solution, is any solution to the non-homogeneous differential equation. Any solution to the full equation. If we find any solution to it, if we can find any solution to it, then the full general solution is going to be the sum of the two. So our job is just to find one, just one solution to this differential equation, and we will have the full, most general form of the solution to this full equation. Remember, the reason that's a little bit, it's important to say that because we realized that this had like a few different solutions, right? You could take any linear combination, and in order to find the full form of that, it took a little bit of work. It turns out we don't have to go through all that work here. We just have to find one solution to this thing, all right? So let's go ahead and do that. All right, so we're going to find xp. I'm going to assume that xp is of the form, we went through the trouble of finding this for a reason. I'm going to assume that it is of the form a times sine of theta plus phi. Some amplitude times a sine, theta plus phi. What does that mean intuitively? I'm saying that if my forcing function looks like a sine wave, oh, that was a cosine wave. Let's move my y-axis. Bring this back down. If that is my forcing function, this is f as a function of time, f naught sine of omega t, frequency omega, here's time. I'm claiming that my particular solution needs to look just like it basically, but shifted a little bit. I'm going to go ahead and use a minus sign here, actually. Shifted over with a minus. I'm going to say that it is out of phase. It's shifted. So let's see. Yeah, something like that. So we're starting negative. We've shifted this thing over to the right. That's what this minus phi is. The phase is that. Okay, and this is my xp. And it's some amplitude. I need to figure out what that amplitude is. But I'm claiming it's the same shape. That's the important part. It's the same shape. Okay, so let's go ahead and figure out what A and phi need to be in order to make that true. We're going to follow the same sort of method that we have in the past. We're going to figure out what A and phi must be by plugging it into this solution here. Okay, so that's xp. xp dot is a cosine of theta minus phi, and xp double dot must be a sine of theta minus phi. Oops. Gosh. let's actually be a little bit more careful here. I don't want that exactly. Sorry. Let's start that over. Let's start that part over. Okay. I'm going to claim that my particular solution is going to be of the form a times sine of, here we go, omega t minus phi. That's what I'm saying. Notice that it looks kind of similar to what we did over here. I'm going to go and let's find out what A and phi need to be in order to make that possible. All right? So I'm going to take the derivatives, xp dot, so I can plug them into the equation here. This becomes a cosine of omega t minus phi. We need to pull out the omega there. That's a omega. And xp double dot is equal to a times omega squared minus sine a negative omega squared sine of omega t plus or minus phi. All right, let's go ahead and write this all out. We have negative a omega squared sine of omega t minus phi times m, negative m a omega squared sine of omega t minus phi, plus c times a omega cosine of omega t minus phi, and plus k a sine of omega t minus phi. That has to all equal f sine of omega t, f naught sine omega t. All right, I'm going to start, let's go to the top here. All right, let's group terms. We've got a ka sine omega t minus phi and a minus ma omega squared sine omega t minus phi. Let's go ahead and group those. We've got ka minus m omega squared. Let's factor out the a. Sine of omega t minus phi. And we've got a plus a c omega cosine of omega t minus phi is equal to f naught sine omega t. All right. We can use that. We can use that. It gets a little bit confusing, but I'm going to call this here lowercase a. I'm going to call this here lowercase b. And let's go ahead and replace this over here. We'll say this, we'll change the name of that variable. This is f naught instead. There we go. F naught, and if we make theta, we turn that into, let's call this theta. Okay. So that's theta minus phi, and that's a theta minus phi. All right. Then basically we have something of exactly the form we need it to be. Actually, excuse me, we need to make this the A and this B. That's better. Okay. Then we have an answer to this. This is possible if F naught is equal to a squared plus b, square root of a squared plus b squared. So F naught has to be equal to the square root of a squared k minus m omega squared that squared plus that a squared c omega that squared. We can factor out the a here. That's coming from both terms. So that's equal to a times the square root of all this jazz. It's k minus m omega squared that squared plus c omega that squared. That's equal to F naught. And so we found that a has to be F naught over the square root of k minus m omega squared itself squared plus c omega that squared. That's what the amplitude is going to be. The amplitude is going to be proportional to F naught, but it's going to have all this jazz on the bottom. Okay, and likewise, we're going to find the phase. So in this case, phi. Here's our A. So it's arctangent of A over B is the arctangent of, excuse me. Oh boy. That's A. This here is the arctangent of AC omega over a k minus m omega squared. Well, really, we can get rid of these. Those a's are gone. All right, and so we have the amplitude and the phase.